Hi, everybody. Welcome to Goblin Talk, the show that I just can't seem to think of a better name for.
It's a good name.
I'm here with the perpetual Alden Eberhardt.
What?
And we have a new guest today. This is Steven Mellard. Am I saying that right?
Yep, you got it.
Normally I just call him Steven. So
Hi, Steven.
Yes.
Zooming to us from Vienna, Austria, which is why we're doing this at a weird time, because it's like 6:30 where you are right now, right?
Yeah, it's the 6 hours ahead of the East Coast.
I have an angry cat in my lap. I'm sorry if there's some weirdness in this, because Isabel got spayed yesterday, and she's not taking it well with the comb.
Not a happy customer.
The e-collar, the lampshade, poor thing. So the only way I can get her to sleep is by sitting in my lap. So she's kind of right here. So we're here today to talk about. Well, let me start by saying we're going to start a series on Goblin Talk where Alden and possibly Joe Cabo, if he can sober up long enough, we're going to talk about the outer planes. Because planar travel is a big thing in Dungeons and Dragons, and the outer planes are extremely interesting to me. We'll probably start. There's limbo, there's the elemental planes, there's no, she's trying to kill me. Okay, there's and so I thought we would have my very good friend Steven Mellard on, because Steven is a physicist. And perhaps he can tell us about the possibility of in real life planar travel or extra dimensions, that kind of thing.
Sure.
I read a little bit about it myself recently in preparation for this. Large Hadron Collider, of course. They're trying to discover gravitons and things. So, Stephen, my first question to you is, what do you think about the weasel theory?
You're gonna have to enlighten me on that one. I don't think I've heard of the weasel theory.
Oh no!
Apparently, Alden can.
I think that this is the whole thing. Is that the Large Hadron Collider? They're working on it, and a weasel crawled up into it. Is that correct, James?
Yes.
And then they're saying that that's why our timeline has been so awful. So we've been shifted into the worst case scenario.
Yeah, we've been shifted
that
to
damn weasel.
So like anti-Pangloss then, right?
Exactly,
like the opposite of the best possible world.
Exactly.
Yeah, we got shifted into an alternate dimension. Obama was president. Everything was mostly okay. And then sometime in the middle of his presidency, everybody remembered the Berenstain Bears wrong. And and everybody thought Nelson Mandela was dead. Yes, exactly. And it was all due to the Large Hadron Collider.
Yes, actually, I blame the Kingpin for this. He's been messing around underneath New York City.
Oh yeah,
bringing all the Spider-Verses together.
Hey.
Yeah.
Oh yeah, there we go.
Maybe.
Yeah.
That's all his fault.
It's all Miles Morales. He's the only one that can save us.
Exactly. So my name is Steven Mellard. I went to school at the University of West Georgia and at Georgia Tech. There I got the degrees in physics, mechanical engineering, and radiological engineering. So my specialties lie in neutron transport and transmutations of elements, nuclear detection. So I will do my best to answer your questions today.
We're very glad to have you here, because normally we just sit here and talk about nonsense, and it's nice to have somebody who knows what they're talking about when it comes to nonsense.
And hit me with the first shot.
Alden Eberhardt's no slouch.
That's not true.
He's no slouch when it comes to academia.
Yeah, how dare you?
Actually, it's a funny thing. When I was taking classes at Georgia Tech at the time, this was like 2012, 2013. The Princeton Review released a list of 1,500 schools rated from most manageable course load to least manageable course load. I remember MIT got something like in the 900 region, and Georgia Tech was about 1300. So it was.
No
When
kidding.
it comes down to manageability, they really like to pile on that homework. I mean, Alden, I bet you can really just
Yeah, Alden.
commiserate with me here.
Went
They had
through
a
his
great
text.
resources in order to you could call in a TA and there was a channel that you could watch him and he would do homework with you. And that was really cool, but we would goof off and just find really hard problems for him to solve.
Yeah.
That's why I didn't do well.
I just remember all those weekends programming in MATLAB. It just take me 13
I
hours.
hate that. It's bad. It's a bad program. No,
Yeah.
it's meant to be different.
I'm actually
Sorry.
doing something similar with a different program right now. So I've been
Yeah.
screaming and throwing my laptop all day.
Yeah, you guys are both super smart. So maybe we can figure out how to move into another dimension or something.
Let's do it.
During this.
Oh, you mean I
myself am I'm an aircraft mechanic.
Hey.
I have an A&P license, and I'm about 3/4 of the way to an English degree. So you guys are gonna have to pull me through this.
Sure, I'll use big words.
And
Yes, please do. You don't have to dumb it down for our audience, Steven. Because anybody who follows Neon
No, I have
Goblin
great respect for your audience.
or is watching, they are smart as fuck.
Yeah.
Okay. So use as big words as you like.
So the space between the neutrons symbolizes the emptiness in man's soul, James.
Okay, so I guess the first question is, what is a graviton and what does it mean? Why are they looking for it?
So a graviton is a theoretical particle. That means that there is mathematics. People can juggle math around and come up with all these different numbers. But that means that there is not yet any empirical evidence. Take the Higgs boson. In the last decade, that was one of the major spheres of research for CERN, right? The Large Hadron Collider. Was designed to find something called the Higgs boson. The Higgs boson was theoretical for many years from the 60s. When I think it was Dr. Higgs first theorized it, and they did not. They felt like, I think it was 2012. They felt that they had enough conclusive evidence to declare that they had found it. There were some irregularities. They didn't find it exactly where they thought it was going to be, so that was actually quite interesting. I think it was don't quote me on the numbers here. I don't know off the top of my head, but it's in the big Electron Volt region.
But they did find it pretty soon after turning the thing on, right? I mean,
yeah, actually, and
it was almost right away, right?
It actually took a couple years before they actually got it. But 3 or 4 years, because it's a really large machine, and getting everything fine tuned and getting all the screws tightened down onto it takes some time. But that was really important because that was the subatomic particle that attributes mass to an object. So not every subatomic particle has mass, and the Higgs boson is a subatomic particle that interacts with something called the Higgs field, which is I don't think I have the finesse to describe exactly what it is, but it's essentially a tensor field. Which is, and the particle itself interacts with this field and causes, for lack of a better word, a resistance or friction, and that's what causes the particle to have mass and to be slower than light. So anything that doesn't have mass travels at the speed of light, and anything that has mass, that is, has a Higgs boson, travels less than the speed of light, slower than the speed of light.
Okay.
The graviton is a theoretical particle that links objects together, links subatomic particles together, and that it has that its gravitational influence is it's like what you call a carrier particle, a transfer particle, and something called the Standard Model, which is the most advanced scientific understanding of particle physics. It links 3 of the 4 major forces in the universe. That is the electric is going to be the electric field or electromagnetic. It links the strong and weak nuclear forces. The strong force is what binds the nucleons and a nuclei together. So you have like protons and you got neutrons, and they stick together because of the strong nuclear force. The weak nuclear force governs radioactive decay. So when you have a particle, for instance, you have a neutron that decays into a proton and a electron, the electron can then shoot away and release some additional, we call a mass and momentum balance, something called I believe it was a neutrino, something that it kind of helps balance that equation. So there are two very important rules in the universe.
So what you're referring to is called the standard model of particle physics, right?
Yes, it's a standard model.
With those four forces.
But it does not actually link gravity. That is the one.
Yeah, that's what I was reading about, is that gravity doesn't really fall in line when you're looking at the standard model.
Also, there's when you start looking at physics, you can group them into very large objects, the physics of very small objects, the physics of very fast objects, and the physics of very slow objects.
Such as Alden walking on a tightrope, right?
Very slow.
And then an ant actually circling the tightrope, because the ant can move in more dimensions and back and forward, right? Which brings us into the other dimensions that are around us, apparently. They could be very, very small that we can't see, or they can be. Am I putting that correctly?
So some of the first, I guess, some of the first hints that this theory has some momentum actually came back in the early parts of the 20th century. Experiments into what's called the double slit or interference experiment. That is, so light travels as a wave, but it also has properties of a particle. So when you look at, we do something called the double slit experiment. You have a dark box, and inside, on one side, you have two small slits. And when you shine a light, what happens is the wave front moves up to these small slits, and they create new wave fronts from these two slits. So you have waves that will then overlap and cause patterns of interference. We call it constructive or destructive interference. So you get these bands of bright and dark slits or lines on the opposite side of the box. Well, that's all fair and good. That kind of proves that the light comes as a wave. However, as new instruments became available, more sensitive experiments, there became a problem, because there are something called I think it was called a work function. That is, scientists in the early part of the 20th century found that it doesn't really matter how much light that you cast on an object. Actually, let me rewind a little bit, because I had something called tell you about this work function. So this work function has a photoelectric effect. It means that when you shine a light on a metal, the light will actually dislodge one of the electrons, and you can get electric current out of this. So
yeah, that's how we make. That's the basic idea for like solar panels.
It's part of it, yeah. Actually, it's so you have this work function. This work function tells you how much energy you need from your wave, from your light, in order to break apart this electron. And so in theory, if light is a continuous wave, the more light you pour on something, the more electrons you get off of it, right? That didn't happen. It doesn't work that way.
Oh, really?
It turns out that the color of the light is more important than how much light you have.
No kidding.
Right. And so this kind of gave birth to this idea of Einstein's photoelectric effect. That is, a photon was what he calls a little package of light energy. And,
like a particle, right?
It's a light particle, right? It's a photon.
Okay.
So you've seen this word photon. It comes around.
Yeah.
That's essentially what it is. You're breaking down a light wave into a distinct particle, little packet. And that was really the start of one of the starts of quantum mechanics, right? So if you go even further back, we talk about called the ultraviolet catastrophe. And that was the problem in physics where if you look at a continuous scale, that is without interruption, it predicted that objects that are around room temperature should be radiating with almost unlimited energy. And because we look around, obviously don't see objects radiating unlimited ultraviolet energy, realized that this energy cannot come in continuous form. It has to come in steps and little pieces and chunks.
Okay.
And that was first theorized by Professor Max Planck.
Yeah. Okay.
So you've heard about the Planck scale or Planck. He was the first person to theorize quantum mechanics. He didn't like it. Not a lot of people liked it, but it worked mathematically.
People don't like it now.
Realistic results.
Okay, so that double slit experiment that you were talking about with the light thing, right? The way I understand it, as someone who's 3/4 of the way to an English degree or psychology, who knows?
Right. Could go either way.
Yeah, could go either way. Is that you shine a light? There's 2 slits in a cardboard box or something like that. Some of the photons decide to go through one slit.
Yes.
And some of them decide to go through the other, and nobody knows why they make that decision.
And that's what happened when we developed better instruments. What we started doing is shining just a barest little bit of light, just a couple photons at a time. And what they found is that even if this photon has no other photons to interfere or react with it, it will, as the moment it gets the slit, it appears to break apart, interfere with itself, and then form the same pattern. So even though these photons are only going through one slit, and they're only going through one at a time, they're still interfering with each other. Now, how is a particle be able to interfere with itself? It's only supposed to be able to go through one slit. Well, one of the theories that help explain this is that there's actually another universe where light is going through the opposite slit and interfering across planar boundaries.
So hang on. Okay, so what you're saying is the photons are going through simultaneously. They're going through one slit and both
at the same time. Yes. So imagine if you saw a billiard ball sliding towards a storm drain, and then it splits into a bunch of billiard balls, slides through the storm drain, and they all scatter against each other, form one billiard ball, and then strike the opposite end of the storm drain.
And these other dimensions are what it could explain that. What you're saying?
That is one explanation for why this interference occurs. Is that that overlapping dimensions, the light actually is interacting across all these dimensions, and this kind of gave way to some other theories, experiments. And so this kind of progressed to something called the string theory. You may have heard of the string theory that yes, that all matter comes down to a string that vibrates at very specific frequencies that correspond to quantum mechanics. So you have one frequency gives you one type of energy, another type of frequency gives you another type of property. But one of the real mysteries is, why is gravity so weak? If you look at the strong force, you look at the electric force, you look at the weak nuclear force, they are orders of magnitude more powerful than the gravitational force. In fact, it takes objects the size of black holes, of planets, of stars, for gravity to even have a noticeable impact and influence. So one of the things that the string theory postulates is that the graviton is actually a particle that interacts across different universes, and that's the reason why it's so much weaker, is because it's spread out.
And the extra gravity goes into other dimensions.
Yes, that's just one theory about why gravity is so weak. And so there is actually mathematics to show that if you include extra dimensions, that is, you have you have length, width, and height, and then you go on to other dimensions. And you've heard about tesseract, which is a fourth dimensional cube, meaning that its shadows, its silhouettes are three-dimensional. If you go up to 11 dimensions, you can, in theory, have a particle that interacts across these dimensions and would have a weaker interaction overall than the other more local forces, such as strong the strong force, the electric force, and the weak.
Before we move into those other dimensions, we have a question from the chat that I thought would be interesting.
Yes.
Silver Wolf wants to know if the Higgs boson can be weaponized.
God dang it, Silver Wolf.
So if I recall correctly, its energy is about from 100 to 150 gig electron volts, which means that it is a very large particle. One of the things that Einstein taught us is that energy is directly correlated to mass through the square of the speed of light. So there's a very, so that's how you get nuclear energy, this nuclear power from everything from electricity to light your house, to bombs, to to blow up cities. It comes from this energy to mass conversion. The amount of energy that's released from the fission of a uranium atom is about 200 mega electron volts.
Okay.
And the amount of energy required to smash two particles together to get a Higgs boson out is about 1,000 times that energy.
Oh. So I think the answer is no then, Silverwolf. Sorry.
You would have to have something that is far more powerful than a Higgs boson just to make them in the first place.
So you would, okay. Yeah, so it would be, that wouldn't work out.
So imagine carrying around some the Large Hadron Collider and trying to
you would need a gun that's a mile long.
Right, and you'd have to smash two particles together to even break it loose. So
which
you have to
just
convince maybe if that weasel were able to get in there, right? Like
dang weasel,
somebody
ruined our world.
right. So if you were to lure somebody into the collision chamber and somehow convince them to stand in the beam line, maybe, but no.
Do you remember it as Berenstein or Berenstain? Or is that before your time?
No, I remember. I always thought it was Berenstein, but
all right, I'm with him.
I did too, but I mean, I don't know.
It's the damn weasel, man.
Yeah.
Look, all I'm saying is all of this has just gotten me excited that you guys are getting closer and closer to me getting the heck out of here, and by which I mean this universe.
Yeah, this universe is subpar. I want to go back to the one we were in the 90s.
I get that we're still a very long way away, but I feel like we're living longer nowadays. I'm rooting for you. All right, just get me out of here.
Back before everything got all heavy,
Right.
Back before 9/11. So Steven, what do you think the possibility of humans moving between these dimensions is? Now, I know some of these, like we're talking about gravity going other places besides our, let's call it the material plane, why don't we? That's what D&D calls it, right? So if we're in the material plane and there's all these tiny dimensions, bigger dimensions, things we can't perceive in our 3D world, right? What is our possibility of moving into one of these other dimensions?
Okay, so in quantum mechanics, we have something called a superposition. That is, you have a range of different states, and they all have a different probability. So let's say that I were to trap a ping pong ball inside of a box, right? And it goes back and forth. Right? There is mathematics that can describe its position as a waveform. That is like a sine wave, like you kind of think of when you look on an oscilloscope and you see these waves going back and forth. They can be mathematically, the motion and position of this object be defined mathematically with waves. And so that's what we call a quantum wave form. Now, if you take this into higher dimensions and say, all right, now you have a waveform not just in 3 dimensions, but in 11 dimensions, now you have the probability of that object could be moved around, occupying numbers of different states. Now, according to the theory of quantum mechanics, it is entirely possible for a turkey to essentially tunnel through the material world from a store and appear in your oven for Thanksgiving. There is, according to quantum mechanics, there is a non-zero chance of this happening. Because if you talk about probability and energy, the energy required for this to happen is extraordinarily high. Like it's just stupidly high. But we're talking about in the realm of possibility, it is non-zero. So that is, there is also, if these additional dimensions do exist, in theory, you could have a quantum waveform to move your position from wherever you're standing at currently and to settle or collapse onto a position that is inside, or that is in a different dimension, located in a different dimension. Now, how does that actually happen? That would have to happen with energy. It would, yes, that's the reason why.
That'd be like weaponizing a Higgs boson particle.
Right. That would be like, that'd be like using the transporter as a weapon, right? You just like, you just scan it across and just throw everybody out into space, right? That's kind of the whole whole concept there.
But you're saying there is a possibility.
Star Wars, by everyone, by the way.
All right. So there's something we call a well potential. That is, in quantum mechanics, the object needs to have enough energy to overcome the barriers to teleporting, or to a more appropriate definition would be tunneling. That is, to tunnel through the
like wormholes
barrier and appear on the other side.
Okay.
So let's say if you want that ping pong ball inside your box to appear, what is the probability that it appears outside the box? Well, there is mathematics to describe how energetic that ping pong ball has to be in order to appear on the other side. Now, for an object like an electron that is so tiny, the energy is not very high. In fact, modern cell phone designers and modern cell phone mechanics have to use quantum mechanics to design the circuitry. Because if you have a current, if you have a little flow of electricity,
I read a little about that, yeah.
It is entirely possible for the electrons to just disappear out of the wire they're flowing through and appear in a wire that is adjacent to it.
Interference,
yeah. And so you get quantum interference on your smartphone. So there are steps that have to be taken in order to prevent that from happening. That is, you have to build a potential well between these two wires that is high enough that takes a lot of energy for the electron to tunnel from one side to the other.
An insulator.
Now, yes, it's kind of like a insulator. Yeah, so it's is one way to put it. Well, if you could infuse, so think about that problem is that's very short distances for an object that is very, very small. Its mass is very small. So to teleport a person in that same manner would require orders of magnitude more energy. We're talking like the energy output of the galaxy in order to funnel into this person, in order to get them enough energy to tunnel away from the current location into some other part of the planet, right?
Okay, so let's say you wanted to take, I don't know, something the size of Alden Eberhardt, right?
Right.
And you wanted to plop him into, I don't know, the elemental water plane or something.
Right.
What are we talking about? How many kilovolts?
Kilovolts. Off the top of my head,
you can do watts if you'd
80.
rather.
I actually don't know the amount of energy that we're required to do that. It's been quite some time since I've.
But it's a lot, is what you're saying.
But it is a lot.
Like the sun.
Think about this. You're not even talking about
sun.
this. We're not even talking about a waveform in 3 dimensions. We're talking about a waveform in more than 3 dimensions. So at that point, not only do you have to, not only do you have to have enough energy to move that person, but you have to move them spread across an even larger space. So you talk about a matrix space. So there's this type of mathematics called linear algebra. And in linear algebra, you have one-dimensional space, you have two-dimensional space, three-dimensional space. And there's really no limit to how many additional spaces you can add on to it. So we call it nth-dimensional space. So you say, like, you'll go to 7 or 8, and each of these describe an even greater cosmos. Again, this is just at this point theoretical, and there really isn't any empirical proof for this yet, which is the reason why string theory kind of hit a dead end, and why scientists are really interested in the Large Hadron Collider to crack open new areas of physics for us.
As we keep the weasels out of it.
It would require stellar amounts of energy, and they would also require a way to manipulate this energy to collapse your objects, or in this case, your Eldon's waveform, into a dimension other than where he currently resides.
Now, just to be clear, when you use the word stellar, you mean that literally?
Literally, like
Okay.
the power of multiple suns.
Oh.
In order to, because think about it as scale. Like today, we can manipulate electrons through tunneling. In fact, an electron tunneling microscope uses this exact physical feature of using electrons tunneling through a potential in order to measure, in order to see very, very tiny objects. So we already use this technology. We know it exists. So if you wanted to like teleport somebody to another part of the world,
do you just plug that into the wall?
You'd have to have enough energy to move them.
Do you just plug that thing into the wall? Or do
I
you
wish. No,
that
would sound amazing.
Well, here at the risk of becoming a serious podcast, when are we going to get to where we can use the power of friendship and/or anger, so I can become an anime character? Because that's what I'm looking for.
Well, if you were to power of friendship.
The power of friendship is stronger than the power of anger. We know that.
Well, you find all I need is the way to get the power of friendship into my gas tank.
All right, there we go.
Definitely could use it with all the power requirements that we're going to need in the future.
Yeah.
We talk about it's going to power needs are going to something like increase by a full like twofold or threefold in the next 30 years.
Is that like the opposite of that? There's that theory like about transistors, how they double half in size every certain number of years. Which theorem was that?
You're talking about what was it called?
Is the power requirement the opposite of that?
I
forget whose theorem it is, but transistors are gonna half in size every so many years. We've seen that with cell phones are the obvious example of
that. Talking about on that topic, have you heard of the ITER, the International Tokamak that is being built?
I
like Taco Mac.
In France.
Hold on, I'm gonna look.
I haven't been to a Taco Mac in forever, but yeah.
Oh, it's wow. Yeah, me neither. Being in Austria for 5 months.
Well, yeah, we're in a pandemic, which is kind of the same thing.
Man, I would love to get some fajitas from La Paria again. It's so long. Anyway, actually, the amount of fusion power that is released from a fusion generator is increasing even faster than Moore's law. So it's more than double. It's been more than doubling every year. But the problem is that it started very low back in the 50s and 60s when fusion power was first being investigated. It's gotten to the point now that many scientists believe that with this newest generation of fusion technology, they will finally be able to produce more energy from a fusion reaction than it takes to heat the hydrogen to its ignition point.
Interesting.
So, fingers crossed.
Yeah.
Interesting.
But speaking of energy and energy doublings, that is something that is that kind of correlates to that. Is fusion power has been increasing over the years, faster than Moore's law, in fact. But to talk about the possibility of teleportation, one thing you might be able to do is to reduce the quantum barrier, that is the potential energy required in order to move an object from one location to another.
Okay.
I honestly have no idea how to do that. That is something that in electronics, say for instance, for the electron, this potential well is created by another charge, an electrical charge that opposes the existing charge. So you have potential energy as these two objects are pushed together. In fact, in nuclear physics, we talk about the decay of an atom, releasing something called an alpha particle. And we talk about it according to the strong force and also the electric.
Right.
So there's a combination of the attraction of these two objects due to the strong force, and them repelling each other due to the electric force.
Right.
And the interplay between those two forces gives us our potential well. And over time, eventually, a radioactive particle has enough internal energy that the probability over time is great enough that these two objects will split and the atom decays, or the nuclei decays into a daughter nuclei and into an alpha particle. So it's the potential well comes from a lot of different factors. It can come from the gravitational, electric.
When you're talking about a well, it sounds a lot like when we teach basic electricity. Volt, that's what voltage is. Difference between positive and negative.
Case,
a difference of potential. Is it rated in volts?
It is actually rated in electron volts. So
an
electron volt is the amount of energy it requires to pull an electron through 1 volt of 1 meter.
Okay.
So there's actually a unit of measurement called an electron volt, and it is a tiny, tiny amount. It is 1.6 times 10 to the negative 19 joules.
Okay.
Of energy. So it is a tiny, tiny amount, but in nuclear physics, we measure objects in electron volts.
And that's to move one electron 1 meter?
In electron volts. Yeah. So when we talk about electric fields, we can accelerate an object through an electric field to give it enough energy to overcome this well. So when we actually draw this out, it looks like a particle in a well, and you bring the energy up till it gets over the well, and then you can move it where you want it to go.
Okay, that's kind of like using voltage to overcome resistance.
Yes. Yeah. So you have a barrier that is a resistance, and that's one analogy that you can use for that. And you have to give it enough energy. You have to give enough voltage in order to pull it through that resistance.
Interesting. But it's actually rated in a distance of a meter.
Right, and it's not just electricity that you're trying to overcome.
Right, exactly. You have radioactive particles and things. Because, basic electricity, you're talking about just moving electrons through a conductor. And if you look at Ohm's Law, it takes 1 volt to push 1 amp, which is a coulomb of electrons, 6.28 times 10 to the 18th power electrons, past a certain point in 1 second, right? Whereas you're talking about like actually moving at a certain distance.
Yeah, moving through distance, and take this for instance: is you are attracted to the Earth through gravity, right? So you would have to have. So that's just a start. Is you have to add that into your calculations, that amount of energy is going to require to move you away from the Earth and then to your final destination.
Yeah. Interesting. So what you're saying is, Alden is stuck in this nightmare hellscape that we call 2020.
What he's saying is, I'm safe from your plot to try and get me out of this plane.
I'm trying to help you, Alden.
So that would be what you have to do. You have to either get enough energy to overcome this quantum barrier to tunneling, or you have to lower the barrier in such a manner so that way you can step through or step over this barrier.
Morgan says we're a bunch of nerds. Do you think that, Alden?
She's right, actually.
How dare you?
Is that a bad thing?
Yes.
I don't know. I don't think it's bad.
Hey, being a nerd has got me very far in life.
Yeah.
So I'll take that.
You all the way to Vienna, Austria.
All the way to Vienna, Austria.
I was telling Erica what we were doing. Producer Erica, I was telling her about what we were doing today, and I told her that you live in Vienna, so that we were gonna have to do it earlier in the day. And she was like, "Vienna, Georgia?" I was like, "There's a Vienna, Georgia." It's like, no, I like the Austria. How are your German?
It's been great here. Yeah.
How are your German classes coming?
Ich lerne Deutsch. Ein bisschen. It's Islam song, but
So pretty well. Okay, great.
yeah, it's mostly is.
The only thing I know about Austria I learned from Arnold Schwarzenegger.
Well,
Oh no.
he is one of Austria's more popular citizens. Yes,
He's one of America's more popular citizens too.
Yeah, very
yeah.
true. Governor of California.
Yeah. So, well, I'm glad you're enjoying it there. It's been a while since we got to play D&D. And of course, you're always invited, but we do normally play around 7 p.m. Eastern Standard Time,
that 6-hour
which
time
is
difference is,
that makes it tough.
Is a bit of a potential barrier in itself. Yeah.
I just need someone to tell James why the way he uses his spells is mathematically wrong and also unfair. Please.
Well, tell me a little about that.
Oh, he just likes to reverse gravity us and kill us because he's a jerk.
I don't like to do that. That's Selwyn Marlowe that does that. Okay. That's his favorite spell. Right? And when they came after me for using that spell, who was right, Alden?
You were right. Just because you read about it.
You're gonna come after
fair,
me. You better come
nerd.
correct. That's what I'm saying. When it comes to D&D,
I just don't think
have you ever used that spell in a hallway? Like you just like cast it on one end of the hallway. Because you don't always have to make it go up. Like you can make it go sideways too. Right?
yeah, and I haven't done that yet, but I'm thinking about it.
No.
Yeah,
You just like put on the wall, and so so the hallway turns into a it turns into a pit.
I mean, if I land cool like the guy in Inception, I'm okay with it. But if I land on my face, then I don't. This is no longer fun.
Morgan in the chat has a question. Apparently, we'll see. Yeah, I think she's typing. Yeah, that's right, Alden. If you're gonna come after me about D&D rules, you better come correct. That's all I'm saying.
I think it's not fair that you can cast it and then dispel it immediately, and I immediately am just falling.
You can dispel any concentration spell immediately.
Bullshit.
That's how it works.
I just wanted time to cast fly on myself.
You don't get it. Well, man, it depends on how high you went, I suppose.
Yeah.
Yeah, it depends on how high you went. Yeah, Steven was one of the first.
Oh yeah.
Was one of the first DMs I played with after I mean other than like high school.
Right.
And,
actually,
and Steven is a DM that will absolutely try to kill you.
That's good. That's good.
Aww. So which game? Remind me again. Which game was it that you jumped in at? I remember that it was.
We were doing Out of the Abyss.
Out of the Abyss, yeah.
And we were in the Underdark, of course, Out of the Abyss.
Right.
And we had a party of about how many people? With like 6, 7?
There was like 6 or 7. Yeah, there
7
was
people.
There was a good chunk of
This is
people
the
there.
before times when we played in person, and we had to like schedule it forever because everybody showing up in person is even more difficult than doing this. So
of having a large party.
yeah, so it was 6 or 7 people, and we came across Yinagu, the demon lord.
Oh yeah, yes.
And
no,
then the wizard. As everybody's like, we should run away. We're like level 8, I think, at the time, or I was. I don't know about everybody else. We were using
level
rolls.
8 or 9, yeah. I remember that.
We should run away, and the wizard goes,
I think we can take him.
I think we can take him. And you know what? I think he was right. I think, if I don't know, the tide kind of turned, but for a minute there, it looked like we were actually going to be able to take him at level 8. You know what I mean? But Steven, he's smart. He arranges his monsters are not dumb, and they are trying to kill you. That's kind of what they're there to do, right?
Yeah, I would. I'd use them to go after everybody with concentration spells first to knock off concentration. Yeah, and then it's not a proper Yagnu fight unless you have a bunch of gnolls attacking as well.
Right.
So, all right. So Morgan has a question.
Okay, just a question. You got the question.
And I actually think we're gonna get to this later, but Steven, I don't know how familiar you are with the with all the outer planes. But there is.
Oh no, I've been to Sigil.
Okay, great. I know Alden is because Alden's read a ton of old D&D novels. Alden's really familiar with.
Not this particular one though that she has a question about. I have never until your game.
I'm trying to remember the name of it. Oh, by
Bifrost?
No. Bitopia is what it's called.
Okay.
Bitopia.
Yeah, and it's from like a old school D&D, right? And the idea is that there are two. It's an outer plane, right? Bitopia. And the idea is that there are two land masses that face each other with gravity in between. So if you moved up far enough, the gravity would reverse and you go up to the other side.
Okay.
You know what I'm saying?
So I remember there's also a movie that this romantic movie that also had some of the same type of setup. He had two worlds, and they were apart from each other. And okay, so let's see. So in this Bitopia, if you had such a thing could possibly exist if you had if the barycenter of these two orbiting planets, you have to think about it like two orbiting planets, right? And so I actually did take a couple classes in orbital mechanics, which is why I can answer that.
Oh, sweet.
But you have two different masses, right? And 1 and 2, and they both exert gravitational influence on each other. Now, if you give them a spin, they will both, they don't orbit around each other exactly. They orbit around something called a barycenter. So there is a pseudo center, or a little false center to this entire gravitational system. And if that center were close enough to each of the objects, anything on one side of that barycenter would be attracted by object number 1, and anything on the other side of that barycenter would be attracted by object number 2.
Okay.
So in theory, if you could get these two planets close together, you could fall. You could if you get high enough. If you can get high enough in the away from the gravitational pull of the other, the second object will then start pulling you quicker and quicker. But you also run into the problem that if you don't have enough momentum, you could become trapped at the barycenter. It would be something we call a Lagrange point. So you could actually have a station or some fortress that is tidally locked,
or a bunch of people trapped there,
or you could have a bunch of people trapped there. Yeah.
And that was my whole thing, was like, is the whole thing was it showed like the guys in Bipros putting stuff in a hot air balloon and floating it up, and then it would sink like down to the other side. And I was like, no, it would just stay there in the middle.
Well,
and
I think it depends on how heavy the object is.
Would be floating right in the middle.
It would depend on how fast it's moving, because you have to. Because once you get, you have to have enough speed when you reach the barycenter, so that you actually coast to the other side and start falling down at the side. Otherwise, it'll just go back up and then come back down.
How dare I question the
You still have escape velocity. It's still a thing. It's just if you get escape velocity, you just fall back to the other planet.
What if it was something like the inside of a rotating cylinder, like Isaac Asimov? You know what I mean? Like the
something like an what's it called? An ONeill cylinder.
Oh, okay.
Yeah. So you have a long cylinder that's hollowed out, and it rotates to provide centripetal force. And so you get acceleration against the inner surface of the ONeill cylinder, and that gives you a pseudo gravity. But you also get something called a Coriolis force in addition to it. Have you ever seen that TV show that was on Sci-Fi and Amazon called? What was it called? Just off the top of my head. The Expanse.
Yeah. I've seen the first episode. Yes.
Yeah.
A lot of people love that show a whole lot.
In one of the bars, Joseph Miller is up high in Ceres, meaning closer to the core of the asteroid. He's up in this bar, and he starts pouring this liquid from a jar into a cup, and it corkscrews in a strange fashion into the cup. So when you have rotation, you get something called the Coriolis force. And it tends to push you at a right angle to the direction that you're spinning. So
is that toward the ends of the cylinder, or just like around this way?
I believe it's so it pushes you sideways, like a right angle to the direction of travel. So as the stream of liquid flows out, it gets pushed aside. But then as it continues to flow, it continues to be pushed. And that's the reason why it corkscrews down into the cup, because of the Coriolis force. This force is also the same reason why why hurricanes north of the equator spin one direction, and that hurricanes south of the equator spin the other direction.
So if we tried to create
for
a
the same
spaceship
reason.
like an ONeill cylinder, you're saying it wouldn't work out like it
Yeah,
does
is that if
inside
you're
the
walking
levels.
around on the inside, if you'd like,
just be like-
you would be subject to this force of this Coriolis force.
Oh,
One
That's
day,
inconvenient.
when we have one of these space stations, you essentially have to get your Coriolis legs. You get your sea legs.
Oh.
You have
And
to
then
become
you just-
accustomed
You just
to walking around on something that is spinning.
yeah,
Yeah.
it'd be cool.
So you always know the newbies because they're all stumbling around.
Yeah.
going back and forth. Like,
Yeah.
oh.
Letting that right angle force take you,
Yeah.
noob.
Right. And they try to pour something out of a cup and it like spirals off. And it's like yeah.
Well, Steven, maybe next time we do this, we can figure out how to get Alden out of here.
Yeah, really. Oh, wait. You mean into another plane?
There-
Oh, I thought you just meant you were going to bring something smarter onto the show.
There are things
Don't-
that Alden,
Don't
you
send
know,
me.
there are things that Alden likes very much about 2020.
You picked. What are you talking about? No,
And-
there's 0 things.
No, there's at least one or two things
There's
I
one or
know
two.
that you like.
Hey,
Um,
it started off with a great party.
Yeah.
It did, it
Yeah.
really did, and then it was all downhill from there.
Yeah.
So-
It was all downhill from
We need to figure out how to get us the hell out of here. Oh,
You're sending me to the elemental plane of water. I heard what you said. You Freudian slipped it. I'm going to drown there.
but would you rather the plane of fire?
That one, at least I'd go quick.
We're going to be talking about me and Alden and maybe Joe Cabo, and hopefully Steven will jump in with us occasionally as the schedule
absolutely.
permits, about the different outer planes, like Limbo and the ones we mentioned, Bitopia and whatnot, some of the old school ones, some of the new school ones, doing a deep dive, as they say, on these planes. And
Looking forward to it.
planes are a big part of D&D. Like, there's several different spells that can knock you out of the material plane into one of these other planes. So
Yep, and there's been a lot of different ways that these planes have been portrayed in a wider cosmos. There is the wheel concept that you have like an inner wheel and outer wheel. There is there was the Pangea concept where each plane is actually a different area or a different world inside of the same universe. One of my favorites that I like playing with is is kind of like the in-between world where you have we have the Feywild is like a flipped or upside down version of our own world.
Yeah, we went through a period in my home game that has not been streamed where I got bored and started doing crazy stuff. So we've been to several of those planes in my home game, but I don't understand them as much as I'd like to. So I'm going to do a lot of reading on it, and we're going to do it on the show and talk about them.
And it's weird because they're like wonderful places, but every time we visit, just terrible stuff happens. It's weird.
I know. It's the weirdest thing. That's the weirdest thing. We haven't had one single anime beach episode. My home game.
That's all I asked for.
Yeah. Or bathhouse episode, either one.
Yeah.
Maybe we will.
You could throw that one in real quick. Yeah.
Yeah, maybe we will in the future. So, thank you to Steven Mellard for lending some credence to our buffoonery here.
Thank you.
And I hope you join us again in the future. If you hey, if you want to stay up late, you can always play D&D with us. I'm
happy to be your enabler.
Because we do it all remote nowadays because of, there's a pandemic.
Yes.
So you're welcome to jump in whenever you want. Maybe we'll do a show on Saturday where it's earlier in the day.
That'd be pretty cool.
Okay, well, everybody, thank you for joining us for Goblin Talk. I'd like to say thank you to Alden Eberhardt and Steven Mellard. We're both much, much smarter than me, even though I've got glasses on.
I was here to keep the buffoonery on track.
You're very good at it. And we will see you all later.
Take care.
Bye.